So for Module 6, we're basically going to be looking predominantly at acids and bases and what they are. So your acids and bases, remember, from your junior science, you've got acids, you've got bases. You need to know their properties, even before you look at all the more sort of specific definitions that we've obviously need to get into in this module. But basically, from things that you've learned before, you basically understood acids to be things, that are acidic, and you've said that they've got a pH of less than 7, then pH greater than 7. Obviously, that will change a little bit as we go. But we basically said that acids were things that, tasted sour, whereas bases typically tasted bitter. Okay. Acids were things that were sort of corrosive, and bases were things that were sort of caustic. And, acids, we could use indicators, so it turns litmus that originally was blue into red, and bases turn your red litmus to blue. We also say, of course, that bases feel soapy, and drawing in your, drawing in the fact that you've now done saponification, you might understand why, just drawing in your Module 7 thing, because you know what soap is and you know how to make it. You make soap by taking animal fats and reacting with base. So if you feel a base, really you're kind of just making the top layer of your skin soap. That's why it feels soapy, because you are feeling soap, right? So that's why we say it feels soapy, because as far as you're concerned, you are feeling soap. All right. So it tastes bitter, it's caustic, it turns red, and obviously it, reacts with bases, reacts with acids. That's one of the key things of a base. Your neutralization. And your acids also have multiple reactions. So this, reacts with, bases, again, under neutralization. It reacts with metals, assuming sufficiently reactive metals and all that. And we also react with carbonate. Okay. And you'll notice that these are all basically sort of inorganic things, which is why generally acids react more with inorganic. Not to say it doesn't react with organic at all, but it typically it reacts more reactive with inorganic things, and bases react with both as well, but more with organic things like animal fats and so on. Which is why your examples of acids would include like metal cleaners, your stainless steel cleaners, and all that kind of thing. Whereas your example of bases would be more along the lines of oven cleaners, toilet cleaners, because you're cleaning organic matter up there. So that's your typical understanding of acids and bases before this module, or at the start of this module. Now you also need to know your acid reactions. So we'll just quickly write them out. So again, from a junior science or year 11, and this might be part of the revision that you had requested as well yesterday, part of it anyway. So you have neutralization, which refers to the reaction of acid plus base to give you a salt plus water. And this is quite important when you do your titration, of course. And now, as an example, you could have something like hydrochloric acid plus sodium hydroxide being your typical, strong acid, strong base combination, giving you sodium chloride plus water. But if you think about what's actually happening at a net ionic equation level, then this is going to be H plus OH minus to give you H2O liquid. And by examining this, all right, by examining that, it may be quite clear to you, therefore, as a result, that the delta H of this, or in other words, is it endothermic or exothermic? Well, if you think about the fact that you've now got an H plus, like the net result is an H plus plus an OH minus, which is a positive charge and a negative charge, you know, forming a bond. And what that basically means then is because forming a bond releases energy, then you'll get a delta H, which is negative. And this is approximately, you know, negative 57.9 kilojoules per mole. You don't necessarily have to know the exact number, but you most definitely should know it is negative. So that is neutralization. And that's the net ionic equation for it. Let's save a bit of space. Now, we also have reactions with acid plus metal. Now, from your year 11, you understand that metal needs to be sufficiently reactive. And so basically, you know, you need to basically think about whether it is going to, you know, oxidize in preference to acid. So having done the sort of standard tables, you can, if you don't know and you can't tell from your metal activity series from year 11, then you can sort of cheat and refer to the standard reduction tables and work out the E naughts. Again, rely on year 11 theory, but at least you've got the table there. Now, what you also have here is the, you know, you won't really be tested on this part, but I should just mention it to you. The acid is not any acid, actually. You need to be what's called a displacement acid. All right. And as far as you're concerned, basically, the acids you're going to get are going to be displacement acids. So things that aren't displacement acids would be things like, you know, concentrated, you know, sulfuric acid would actually sometimes be what's called an oxidant acid. And, you know, concentrated nitric acid or nitric acid in general is going to be often an oxidant acid and react in an oxidizing manner. So when we talk about the sort of reaction we're about to talk about, you're assuming that it's acting as a displacement acid, which is most acids that you're going to come across. Okay. And that basically means you're going to have acid plus your metal, assuming the conditions are met, will give you salt plus hydrogen. So your typical example might be hydrochloric acid plus zinc will give you zinc chloride plus hydrogen. And if you examine the, you know, the net ionic for this one, then basically it's going to be 2H plus aqueous plus, well, for zinc, it would be zinc to zinc solid, but let me just generalize this kind of like X solid. So it'd be sort of like X2 plus, you know, H2 gas. And obviously, you know, if it didn't have a valency of 1, then, you know, it could be like Y solid to become, you know, Y, 2Y plus, right? It doesn't really matter. Okay, so that's your second one. That's your acid plus metal. Then you've got the acid plus carbonate, which then really is just acid plus carbonate. And you know, you rely on this as well in module 8, and that's why your things aren't as, you know, separated as you think. So acid plus carbonate is going to be used to get a salt plus carbon dioxide plus water. And so we're basically saying that if you've got carbonate meeting with an acid, you should see the evolution of a gas or efflorescence, and that gas will be carbon dioxide. So your typical example might be, you know, HCl aqueous, and we'll add a soluble carbonate, just so that makes it easy for me to justify writing the ionic equation the way I will. So that will give me, you know, 2 NaCl plus CO2 And therefore, going to the ionic equation, that basically means because the chloride and the sodium ions are spectators, you know, being an acid, it's going to ionize. Being aqueous, this is going to dissociate. Being a solution, this is going to dissociate. They will be spectators, and hopefully you're comfortable with that. So it's 2H plus CO3 2 minus, and you'll basically get CO2 gas plus H2O. So this is kind of revision of year 11, but it is also, you know, you are meant to know it for part of module 6. And this particular reaction is probably also helpful for you, you know, in terms of way it relates to other modules. You know, it relates to your sort of module 7, right? You know, when you're trying to, for example, separate your esters, one thing you might want to do is firstly add carbonate first to remove the acid in the mixture, right? So you firstly, you know, you remove the acid by adding carbonate. This also ties into your module 8, right? Just, you know, help you sort of draw links here. You know, in module 8, one of the things you're trying to tell is, you know, if you're trying to analyze in your analysis of, you know, anions, you're trying to tell if there's carbonate, right? And that's why the first thing you do is add H plus, and usually in that instance, nitric acid, for the fact that nitrate doesn't precipitate with anything. But the more key aspect is that you're adding hydrogen ions, in other words, adding an acid to bubble off all the carbonate. So if it's there, you'll see bubbles, and those bubbles will be, you know, carbon dioxide. And if you don't see bubbles, well, then that suggests there's no carbon, or there's no carbonate there. There's no carbonate there, so you don't see bubbles. And if you do see bubbles, it means it's there, but you also get rid of it. So that means there's no more carbonate. And so when you do your later steps, you don't need to worry about carbonate, you know, precipitating out. It'll be some other precipitate, like phosphate or sulfate and so on. Okay, so these are your sort of basic sort of reactions here that you are meant to know. Now I'll pause there for the moment. Let me know if you've got any questions. So with your acids and bases, that's what you've understood thus far. But of course, and that's where scientists were a few hundred years ago. But of course, part of this module, you need to know your definition of acids and bases. And, you know, historically, you know, you've got, you know, different definitions. Try to conserve a bit of space here. So you've got the scientists, and in sort of chronological order, in the order they came up with them. So the first person that came up with a definition was Lavoisier. Now, his definition for acid was that it contained oxygen. And he didn't have a definition for a base. Now, you know, we'll just consider this comments, right? So we clearly know this is wrong at this point in time. Obviously, he didn't at that point in time, but now, you know, this is clearly wrong. And why is that? Well, for example, HCl is clearly an acid, but no oxygen. NaOH clearly is a base, but this has oxygen. So determining whether, you know, it's an acid or not based on whether it contains oxygen clearly doesn't fit in with our current understanding. Having said that, of course, in Lavoisier's time, they hadn't even worked out HCl was HCl. So, you know, that's why it was reasonable for him to say that. And if you were to sort of get an extended response question, you don't really need to focus much on Lavoisier. You can basically say it's the first definition. You can kind of also comment that it's important as it was the first attempt, as it, you know, started the, you know, the attempts. Because otherwise, you know, the attempt of classifying what acids are. So not how they act. So, you know, we've, just like you've been in junior science knowing that, you know, acids react with metals and carbonate, you know, so based on their reactions, we know what, you know, acids do. But until year 12, you never really said what acids were. You just said, okay, this is an acid, this is not an acid, and it does or does not react. And scientists were sort of in a similar situation, you know, a few hundred years ago. They knew what we would say an acid is, but they don't know what an acid actually is, right? And so Lavoisier was the first person that, you know, tried to do that. You don't need to spend a lot of time with Lavoisier. So basically Davy came next, and again, you don't need to spend a lot of time on Davy. And he's the guy that basically worked out HCl was HCl, and knowing therefore Lavoisier is wrong, he had to come with a, you know, better sort of answer. And so his answer was that they contained replaceable hydrogen. And we won't really spend too much time on Davy because there's really not too much to say there. It was kind of an interim. But the ones that you need to know a lot more about start from here. And the next one, of course, is Arrhenius. And he said that an acid was a substance that formed H+ ion in solution, and a base, you know, formed hydroxide ion in aqueous solution. And so this, if you like, was the sort of first sort of more robust theory. And essentially, this is the theory that you've been using since junior science. You may not have known it, but you know, these sort of equations that we wrote on the previous pages, right? You may have come across them in junior science even before year 11, but they've basically just, you know, more or less assumed this, right? So this is a more robust theory. It, you know, allows us to explain quite a few things, explain many things. So one thing it helps us do is it can explain the difference between strong or weak acids. You know, acids or bases. So we'll cover that later, but hopefully you all know that whether an acid is strong or weak depends on how much it's dissociated, like the proportion that is dissociated or ionized. It can also, you know, explain why acids and bases reactions are all similar, because you can think of it in terms of the net ionic equation. So it can, you know, identify the commonality of, you know, acid base, or, you know, reactions of acid bases, like understand it's always H+ reacting, or it's always the OH- reacting. In the case of neutralization, it's the H+ and the OH- reacting. It is also, you know, the first attempt to, you know, define a base, because prior to that, there were no definition of bases other than, I mean, the definition of a base was it reacts with an acid. That was the definition. There was no definition of what a base itself was without reference to an acid, right? And so it would explain HCl by saying that it would form an H++ Cl-. So this is the HCl under Arrhenius version. It would explain NaOH as a base as Na+ plus OH-. But there are a few problems with Arrhenius. So one of the most critical probably is that it is unable to consider NH3 gas plus HCl gas to become NH4Cl solid. So based on the definition here, because it relies you to form, you know, H+ ions in solution and OH- ions in solution, then, well, this is a gas, so there's no ions, right? You never got a chance to ionize, right? HCl is also a gas in gas form, right? I mean, we could have it in acid form, but we could have it in gas form. And when we've got gases, it's molecular, and this is molecular, and there's no ions. But these things react to form NH4Cl. And this we know acts as a base. This we know acts as an acid. So when they're both in air, this clearly seems to be an acid-base reaction, but there's no way under Arrhenius's definition that we could sort of consider that an acid-base reaction because, well, there's no solution involved. So, and there's no H+ ion involved or OH- ion involved. It's just the molecules. So while it seems like it should be an acid-base reaction, the definition doesn't allow us to say it's an acid-base reaction. And so there's a big question mark over that as to, well, if we're going to think about that as an acid-base reaction, we probably should, because in solution that's a base and in solution that's an acid, then how do we define it so we can say that's an acid-base reaction, right? So that's one problem with it. The other problem, there are a few other problems, is that it's unable to explain sort of amphiprotic substances. And the other problem it has is it, doesn't consider the role of the solvent. And so typically most textbooks say that Arrhenius's definition is aqueous solution, which means it's, water. And so some other textbooks may refer to it being in solution and not just aqueous solution. Normally HSC would assume aqueous solution because you don't really do solvents of any others. But I guess the other problem is that Arrhenius's definition is it doesn't consider the role of the solvent, in the sense that however you do define it, what I mean by that is if some things such as, if some substances form H+ in aqueous solution but not in others, then is it an acid or not, right? So if you say that, it forms H+ in solution, but you've got a substance that forms H+ ions in solution in solvent A, but it doesn't form in solvent B, then under Arrhenius's definition, you now have a problem. Is that thing a substance or isn't that thing an acid or not? Because, well, it's the same thing, but in different solvents. And so, we're not really taking the role of the solvent into account. So as a result of that, to try to address these shortcomings, we move on to the next definition. And you can see what I mean by you need to know way more about Arrhenius's relative to Lavoisier and Davy, right? You need to, be able to write equations. You need to see how that relates and so on. And the next one you also need to know quite a bit about. The next science testing question is, well, science tests actually, is Bronston and Lowry. So they both came up with the same theory, basically. And, independently though. And because, back then, a few hundred years ago, you didn't have the internet, things took ages to kind of get around the world. Conferences used to be held, people used to share ideas like once per year, not like, find it in like 15 minutes or less. So, once you wrote your paper, you kind of didn't know what else everyone was working on because, there's no planes at that point in time either. So travel took like months. So they're in separate countries. They're doing their own theory. They both came up with the same idea. And basically their idea was, so that they both get credit for it. The concept of an acid was that it, is a substance that donates hydrogen ions, or ion, otherwise known as a proton, aka a proton donor. And a base is the converse of that, is the opposite. So it accepts H+, which is again a proton. In other words, a proton acceptor. And so we'll comment on this. So firstly, this is a more sort of expansive, so more inclusive definition than Arrhenius. So we're not saying Arrhenius is wrong necessarily, it's just that it depends on what you want to do with it. So Lavoisier is definitely wrong, right? Arrhenius is probably sufficient for certain purposes, and that's why I've been using it for several years. But, it's more inclusive than Arrhenius's. So basically all Arrhenius's acids, I'll just write it as A, are Bronston-Lowry acids without exception. Right? So it's more inclusive. It's basically a subset of Bronston-Lowry now. Different definition, but it's now a subset. So now you'll think of HCl when it dissolves. You don't think of it as dissociating to form H+ and Cl- as we were saying earlier. But what we end up saying instead is that you need to think of it as reacting with water. And that means you'll give an H+ to H2O. And as a result of that, that means you're going to get, you know, H plus, H3O plus, sorry, plus Cl minus. Okay. So you can use, you know, this as a sort of way to kind of show the differences between, you know, an Arrhenius definition where it simply becomes H plus plus Cl minus. Whereas, you know, in terms of Bronson-Lowry, you can see that, well, you've got it in terms of it's turning to become H3O plus. And in a way, it's also more realistic because, well, a single proton is very unstable. So, you know, when we say H plus, we really mean H3O plus in water because it's going to quickly attach to a lone pair of a water molecule. So in a way, it's also, you know, better demonstrates reality. Right. And so now it can explain, you know, ammonium plus HCl. So we'll just take that one that Arrhenius had trouble with. You can explain it because, well, you'll simply just say it's got an H plus there. Now it retains all the sort of ability to explain things like, you know, the strength of an acid that Arrhenius did, but it is also able to explain why things are amphoteric. And if you might remember, that basically refers to whether things can react with acids and bases. So, you know, it's not just reacting with acids only or bases only, but it can react with both. And it can also explain why. So this is something that Arrhenius could not explain, but why neutralize, you know, the salt from neutralization is not always neutral, right? So under Arrhenius's definition, you've got a salt that reacts with an acid for a base. That salt should be neutral, according to Arrhenius. And you know, because you've already done all the theory, that that's not always the case, right? You've got, you know, salts that are acidic, you've got salts that are basic. Typically, metal salts are basic, non-metal salts are acidic, although that's not 100% the case, but that's typically the case. And so for that reason, you know, you're going to have that being neutral. It can explain why salts are not always neutral. Okay. Now, Bronson-Lowry is really the one you need to say the most about. And again, you know, Bronson-Lowry addresses the shortcomings of Arrhenius because if, you know, Arrhenius didn't really specifically think about the role of the solvent, but now, well, we've basically got the role of the solvent, you know, dealt with because you have your acid or your acid to be necessarily having to react with the solvent, right? To be able to do that. And, you know, that's a good point. I should fix that. NH3 is the, just wrote it the wrong way around. So NH3 is the base. So HCl gives the H plus to NH3. Okay. And then after Bronson-Lowry, which is basically the last one that you need to basically know the most about, there is someone else, and that's called Lewis. You don't need to know too much about Lewis. Generally, you're not tested on it, but sometimes, you know, you need to throw one, you know, there's 5 names here. Well, you know, 5 definitions, I should say. More than 5 names, but 5 definitions. And, you know, sometimes you're asked to talk about Bronson-Lowry, Arrhenius, and then, you know, 1 or 2 other ones. So, you know, it's just good to have them on hand, but you don't, you know, the focus, ones you need to focus on are Arrhenius and Bronson-Lowry. So this is, on the other hand, again, basically it did to Bronson-Lowry what Bronson-Lowry did to Arrhenius. You change the definition. So this is a electron pair acceptor. And this is an electron pair donor. So it expands it even further. So you're not only talking about H plus, you know, anymore. You're not talking about protons anymore. You're talking about electrons. And again, you know, all bronze-similarity acids are Lewis acids. Okay. And it expands on the definition even further, but we won't need to get too much into that. So make sure you do know the definitions. Okay, we've more or less ran through the definitions and what they are. As you can see, Arrhenius and bronze-similarity are by far the most important. We've outlined the key sort of things that each one does and does not do, their limitations and so forth. And, you know, for a, you know, multi-mark question, you know, anything from like, you know, 3 to 8 or 9, you will need to go into varying levels of depth about that. And, you know, if it's a very mini mark question, you may want to include sort of equations, for example, like these and these, to demonstrate, you know, how they approach the same situation differently. Good. So addressing certain concepts, you need to, of course, be very clear about the difference between the strength of an acid and the concentration of an acid. So the strength of the acid basically, as we said, is, you know, introduced by Arrhenius. So in short, this refers to the sort of degree of ionization. You know, of an acid. So basically, you know, if you've got something like HCl, which is a strong acid, we essentially, you know, let's sort of do it that way. So we've got HCl. We're saying that it's become H plus plus Cl minus. So this is basically, you know, now that you understand equilibrium, this is basically 100% ionized, or we think of it that way anyway. So we say it's strong. And a very typical example is your acetic acid. I'm just going to use Arrhenius to sort of help me reduce the amount of writing here. And yeah, I should strictly put in states. And, you know, this might be something like 1% ionized. And this is therefore classified as weak. Okay. So the concentration of the acid, on the other hand, is simply just talking about, you know, the amount of, you know, solute in the solvent. So just how much you dumped in. That's all it is. So, you know, it's just definition, N over V. So these two things are completely different to each other. So you've got the strength of the acid, described in words. You've got either the case of a strong acid or a weak acid. And you've got concentration, which is described as concentrated, or, you know, or dilute. So you've got these different cases here. So using, you know, qualitative terms here. So clearly, if you've got so hopefully, you know, on this side, this is going to be, you know, high strength, or we'll just say strong, but I guess this is, you know, high concentration. And it's going to be low concentration. Okay. Now, so obviously, you know, that just means quantitatively, H plus or H2O plus is high. I mean, you guys know that. And in terms of strength, it's basically degree of ionization. So one way to look at it is, you know, percentage of is high, and this is percentage is low. And so whether something is strong or not, basically just depends on what type of acid it is. So for example, you know, HCl is strong, so HCl is strong. Doesn't matter if it's, dilute or not, as long as it's HCl, well, it's HCl, so it's strong, right? And as long as it's, say, acetic acid, then it's weak, just by the nature of it being acetic acid. But the concentration could be high or low, and that could be something very similar to, if it's very high, then let's just say 1 mole per liter is high. Not sure you can even dissolve acetic acid that much, but just to demonstrate the point, the same concentration, so that might not be actually possible, but you get the point. It depends on just the concentration. We don't care about, what it is, and dilute could be something like, So the concentration only cares about the concentration. It doesn't care what it is, right? If we're talking about the concentration of the acid. And if the, whether it's strong or weak, just cares about, the concentration cares about the concentration number, and the strength of the acid just cares about what the acid is. Now, the strength of the acid refers to, I guess, how much it's ionized. So given what we've said yesterday, it really is talking about how much to the right you go. So it's really, we've expressed it thus far today as talking about the percentage, and it is trying to represent that. So it is trying to represent, how far to the right you go. So, it's saying, okay, we've got, 1% products, 99% reactants. But you might recall from yesterday that that can be because it's equilibrium. It's a reversible reaction. One way to represent that is we can use K to represent this. And that's why, whether we use Arrhenius' definition or Bronsted-Lowry's, which is adding water, it won't matter. Our K will therefore be, H plus times CH3COOH over CH3COO minus over CH3COOH. If it was Bronsted-Lowry, this will become H3O plus, which is the same anyway. And you've got a water, which we'll ignore anyway. So it'll still be the same. And as I briefly mentioned yesterday, this is your Ka, but that is just your K, right? So another way to consider strength of an acid quantitatively, other than percentage, ionization, is to also consider it from a Ka point of view. And so, think of it this way: if, because we want K to go up for more to the right, and more to the right being more ionized, so this would alternatively mean that Ka would be a big Ka, and this Ka would be a small Ka, or Kb for that matter. So I'm focusing on acids now, but obviously there's an equivalent for base, right? So this is Ka, high Ka, and this is low Ka. And because we're revising, I assume you guys know this. I'm, kind of just throwing concepts as we go. So you might also recall, and I'll write this on the left, that pKa is negative log base 10 of Ka. And so as Ka goes up, I think all of you do 2-unit maths and above, so you should be comfortable with log. If if Ka goes up, then log of that number goes up, because log's an increasing function, but there's a negative in front, which means it's going to go down. So that means pKa is going to go down. So all of these things are equivalent, right? And of course, this one, pKa, is going to go up. So basically, the strength of the acid is, by definition, how much the, acid has dissociated, or the base for that matter, if it's a base, but we're talking about acids here. So that basically means, well, percentage to the right goes up, that's by definition. Percentage for strong, that means, considering what Ka represents, Ka is going to go up. And considering what pKa represents, that means pK is going to go down. And very similarly for weak, just all the opposites. And you'll notice that none of that has anything to do with concentration. Concentration is simply, N over V. And actually, I wrote the wrong thing here. I probably should be writing HA, because I need to talk about the difference between HA and H plus in a moment. So I should actually be writing for the acid more accurately for the acid. Okay. All right. So the key points that you want to understand from that is that, you know, strength is different to concentration. So, you know, it's a bit like, you know, proportion versus like, you know, so it's a you know, like strength is like, you know, your accuracy, right? So, and concentration is like how many hits you've taken. So, you know, you might need to, you know, you might have thrown like, you know, 10 darts and got 10, you know, 10 bullseyes. That means you're really accurate, right? But you could have thrown 1,000,000 darts and got 10 bullseyes. Well, if you throw 1,000,000 darts, you're very concentrated, like you tried a lot of times. But, you know, you didn't really get many hits. So strength is like the proportion. Did you hit 100% of the time, or did you hit like, you know, whatever, like 0.00% of the time, right? So strength is all about percentage, and concentration, think of it kind of like, you know, like, well, it literally is just amount per unit volume by definition. Concentration, well, of the acid anyway, is simply just calculated by N over V. That's all it depends on. Whereas strength, you know, depends on how well it dissociates or ionizes, depending on if you're talking about a, you know, acid or a base, and that can be represented quantitatively by Ka, or alternatively pKa. And, you know, for a base, that will be the equivalent, so K being pKb. But it's essentially the same. Okay. All right. So, you know, note that if you've got, you know, HA, as we kind of said earlier, I'll just rewrite this out again. We've got HA to become H plus A minus, or alternatively with the other definition, it won't really matter. That is going to, you know, both of them will give you a Ka of H plus times A minus over HA for both of them. Good. So this is then often confused with pH, and you might recall that by definition, pH equals negative log base 10 of hydrogen ion concentration. So basically, pH is simply a log scale of hydrogen ion concentration. So it's not really any different, all right? pH really is just telling you that hydrogen ion concentration, but with a number that, you know, might be nicer, right? Rather than having numbers going from 0.00000 blah, blah, blah to like, you know, 1.4 or whatever, you know, or anything higher even, you just get it, you just take a log, so you have a rough idea, right? And so the converse of that, hopefully you guys are all happy with this, and you should be, but basically, if we rearrange, we just get H plus must equal 10 to the power of negative pH, all right? So, you know, these are sort of formulas that you're meant to know. I believe they're on the reference sheet, but you should be more than comfortable with that. Now, note that the concentration of H plus is influenced by multiple factors. Well, clearly, it's going to be influenced by the concentration of the acid. So the more concentrated the acid is, then, you know, assuming, you know, then that means H plus will also go up, all right? But they're not the same. So the concentration of the acid, well, unless you're talking about a strong acid where, you know, if you've got something like HA and it's monoprotic, we'll get to that. But if you're talking about something like HA, not all of it goes across, then the concentration of HA is not going to be the same as the concentration of H. So, you know, that's one thing you need to recognize. They're not necessarily the same. Now, even if there's a strong acid, you still need to take other factors into account. So the second thing, of course, we kind of mentioned here is the strength of the acid. So if it's a strong acid, it makes it a bit easier. You don't need to worry about what percentage you went across. But, you know, it's the combination of the concentration and the strength that tells you how many hits. So it's like saying, how many times did I try to throw the dart? 100 times. What's my accuracy? All the time, 100%. Well, that's easy. I throw 100 times, I hit 100 times. But if my accuracy is like 23%, well, then I got to consider, okay, I threw 100 times, 23% accuracy, so I hit 23 times. Yeah. And then, of course, the other thing we need to consider is whether, you know, the, you know, number of protons per acid molecule. So is it monoprotic? Is it diprotic? Or is it triprotic? And so on. So this basically means 1H plus, this means 2H plus, this means 3H plus. And you might also come across the term polyprotic, which is greater than, you know, 2, greater than or equal to 2H plus, multiple, okay? So, you know, something like hydrogen chloride, hydrochloric acid is monoprotic and strong. Something like, you know, carbonic acid is diprotic and weak. Something like phosphoric acid is going to be, you know, triprotic and weak. And speaking of that, you probably should understand which ones are strong acids. So your obvious ones are hydrochloric acid, nitric acid, and sulfuric acid. They're considered strong. And then your other less tested ones, but still can come up, especially on the new HSC, is hydrobromic acid, hydroiodic acid. Last one, so, you know, those are the ones that you probably should be expected to know are strong. Okay. As far as weak acids go, well, basically, unless you're told otherwise, you assume all others. But basically, you know, obviously it depends on the actual Ka and so on. But generally, you assume all others are considered weak. But your typical ones are, of course, your, you know, ethanoic acid and all the other ones from module 7 as well. And you also have, you know, citric acid. And by the way, citric acid, you should also know, is triprotic. And you should sort of be able to draw out the structure of citric acid as well. You know, if you have questions with regards to citric acid, we will perhaps, you know, draw out the structure in more detail when we go through organic chem, but that is something you are meant to know. Okay, you are meant to know it is an acid, it is a weak acid, and it's a triprotic acid. And you are meant to know its name, and you are meant to know its structure. Okay, so you need to consider all of these things, which will then help you determine the concentration of H+. Once you determine the concentration of H+, then of course you can just take the negative log base 10 of that number to get pH. And therefore, that will be pH. So we'll also need to quickly cover the idea of what conjugate acid bases are. Now, conjugate acid bases, remember, relates to the sort of Bronson-Lowry definition. They don't exist under the previous definition. And basically, under Bronson-Lowry definition, you've got an acid plus a base react to form something. But the point is that, well, the acid is going to give NH plus to the base. So that means because the base is going to accept an H plus, you're basically going to end up with, you know, the base plus an H plus. And you'll end up with the acid minus an H plus. Those are your products, all right? And so we consider that this thing here, this will be considered the conjugate base of the acid. And this will be considered the conjugate acid of the base. So typically then, that is what that basically then means is that, well, you know, your conjugate acid is just, it's a relationship word, right? So, you know, if you want to work out conjugate acid, so let's say I've got OH minus, and I want to, going to the right is the conjugate acid, say, I just add an H plus, so that makes it H2O. So this, so in other words, H2O is the conjugate acid of OH minus, and we could keep going for that matter. So add another H plus, and it's going to give me H2O plus. And so, H3O plus is the conjugate acid of H2O. And it's a relationship word. So, the opposite is also true in the sense that, so OH minus is the conjugate base of H2O, and H2O is the conjugate base of H3O plus. So, going this way, you're looking at conjugate bases. Similarly, you could say HCO3 2 minus has a conjugate acid of HCO3 minus, which is a conjugate acid of H2CO3, and H2CO3 has a conjugate base of HCO3 minus and HCO3 2 minus, and so on. So hopefully that's not a concept that confuses any of you. Now, this conjugate acid base is going to be quite helpful though, because when we talk about amphiprotic substances, by definition, this is a substance that can either accept or donate H plus ion, okay? And so something like, for example, H2O, and in other words, basically, another way to put it is it has both a conjugate acid and base. So, H2O can clearly, go this way to become OH minus, which itself can become O2 minus, but let's not focus on that. It can also go this way to become H3O plus. So that's why, your H2O is amphiprotic, right? Whereas, sometimes Cl minus cannot, just can't donate H plus. So it is not amphiprotic. Now, there is often a, confusion between amphiprotic and amphoteric. And I suppose because the words look kind of similar, and I suppose also because, well, their concepts are sort of similar as well. But essentially, an amphiprotic substance is a substance that can either accept or donate an H plus, whereas amphoteric is simply a substance, that can react with an acid or a base, like either or. And you might look at those two definitions and say, well, they're more or less equivalent, and you might be right for the majority of the time, I suppose. But there are substances that are amphoteric, which means that they can react with both acids and bases, but they are unable to react with, they are unable to donate H plus, right? And examples of that would, for example, be zinc, right? Zinc is a metal. And if you react it with acid, it will create hydrogen gas, and you can actually react it with base as well, and it will create some sort of zinc hydroxide thing. And so it has the capability to react with both acids and bases, but clearly there's no H plus to give away, right? Sure, it has a nucleus, but it's not going to change. It's going to remain zinc. So therefore, zinc is an example of something that's amphoteric, but not amphiprotic. Having said that, all amphiprotic substances are amphoteric. So it's like, amphiprotic is a subset of amphoteric. And this term is something that I guess, many books and or teachers, get confused about. And, and so, look, there is a distinction, but make your judgment call if you see it in an exam paper or a trial in particular. Hopefully not so in the HSC. But yeah, because these two terms get mixed up a lot, even, you know, and in books and teachers, then, you know, perhaps demonstrating, if they use the word amphoteric, but perhaps demonstrating amphiprotic is sufficient for their purposes. Like, there is a distinction, but, you know, sometimes they meant that, potentially, depending on, you know, yeah. All right. So that's your conjugate acid bases. Now, that also, by the way, as a quick, you know, extension, is how your indicators work. So we know that indicators work, or their point of view is that your indicators are intended to help sort of distinguish, you know, between, you know, how acidic or basic a substance is. And so, you know, you're meant to add an indicator to a substance, and if it's very acidic, it will hopefully show you something, such as one color. So, you know, the common thing is, you know, you understand that you've got, you know, acidic color range, you've got the middle color range, the change range color range, and you've got your basic color range. So you've got, you know, for example, for litmus, you've got red, purple, you know, blue. For example, for your, you know, phenolphthalein, you know, you've got your colorless, and then, well, sort of light pink, I suppose, and then pink, right? For methyl orange, you've got your red, and you need to know all of these, by the way. And then, you know, you've got red, and then yellow, and then, you know, just remember that the middle part is always the mixture, right? You've got red, yellow, orange, and so on. Okay. And so you need to remember that you know, for titration purposes, you'll need to know your different sort of colors, and of course you also need to know bromothermal blue. Okay. And your bromothermal blue is going to be blue and green because it, you know, mixes with yellow. So typically, you know, commonly use colors to distinguish. There are indicators that aren't using colors, but, you know, our focus is, of course, on color ones for now. Now, I was going to focus more on how things worked, so I'm not really going to go into this here. Well, I might as well do it at the same time. Just make sure as well that for each one, you know what the change range is. So, you know, litmus is going to be around 7. I mean, obviously it's not actually 7, but it's more important for you to know around the sort of, you know, where it changes. Phenolphthalein is in the basic range, so around like 8 to 9. Methyl orange is around the 3 to 4 range. Bromothermal blue is again around the 7 mark. And bromothermal blue, you know, has a narrow range compared to litmus. Okay. Now, the thing is, how do these work though? And it might sort of help you to sort of understand a little bit of the concepts behind them, but you know, memorizing that is important. Well, an indicator basically is made up of a weak conjugate acid-base pair. So imagine I've got a weak acid. Such as HA. And for now, I'll just use arrhenius because it really doesn't matter. And you know it's become H plus A minus. And so this is the acid, obviously, which is weak. It needs to be weak for reasons that will become apparent very soon. And this is the conjugate base of that acid. Now, if you have this and this. And let's say that one or both of these have color. So let's say that this is, you know, hypothetically, this is red, all right? And hypothetically, this is yellow. So you can probably see that, you know, think about what happens if H plus ion concentration goes up. So if H plus ion concentration goes up, then, well, you know from all our work before, and this is why I keep telling you module 5 is not just module 5. The concept is important. So if you increase the concentration of H plus, or another way to think about it is if the pH goes down, same thing, right? Equivalent, right? So if pH goes down, which is the same as H plus goes up. So either, you know, and that basically means it's acidic, you know, all the same thing, different ways to express the same thing. What that basically means is that, you know, H plus goes up, so it's going to shift left, right? We all agree with that. Now, if it shifts left, then you're going to have a lot of this and not much of that. And so it's going to look red. And, you know, if the pH goes down, pH goes up, which means, you know, H plus ion concentration goes down. And in other words, if we're looking at basic conditions, then you're going to shift right. And then in this situation here, given that, you know, I've got yellow on this side, that's going to look yellow. And, you know, obviously, if I'm kind of halfway in between, both of these will exist in sort of appreciable amounts. And red plus yellow gives you orange, which, well, seems to be basically how methyl orange works, as an example. So essentially, an indicator basically takes advantage of equilibrium using the fact that, you know, different substances, you know, have different sort of, you know, change ranges and Kas and so on. And therefore, and as long as one of them has color, so something like phenolphthalein only has color on one side, but no color on the other side, but, you know, it's still useful as an indicator. As long as at least one side has color, then that's how indicators work. And this, in fact, essentially is very similar to the concept of a buffer solution. So the first thing of what we need to talk about with a buffer solution is, well, what it is, or what its function is. So I guess there's different ideas of what a buffer solution is. The first idea, of course, is what the function of a buffer solution is. And if you guys know what the, you know, what buffer means, like buffer is kind of like a margin, like a leeway. So in other words, the function is a solution that can maintain the pH within a relatively narrow range, you know, despite the addition of small amounts of acid or base. So we're basically saying that, you know, when I say small amounts, you know, obviously if you add too much, then, you know, obviously you're going to overcome the buffer solution's effect. But the point is, a buffer solution is one where you can add a bit of acid or a bit of base. And will the pH change? Well, yes, it will, obviously, but not much. In fact, sometimes not much at all, depending on, you know, obviously how much you added. But the point is, it you know, compared to something that's not a buffer solution, it changes a lot less, a lot less, right? Basically, it's kind of like something that can sort of, you know, it's got a bit of flexibility and leeway. You can give it a bit more, you can give it a bit less. It's got a bit of tolerance. It's not going to complain, right? It will deal with it. So think of it, you know, one way to think of it is a bit like, you know, you've got, you know, if you've got buffer, it's a bit like your clothes. If your clothes have a sort of, you know, if it's not very tight fitting and you can kind of tighten it or loosen it up a bit, then whether or not you get, you know, if you eat a bit more and you're, you know, a bit full and your girth has increased a little, you can still, you know, you're still reasonably comfortable in the clothes. And, you know, if you get a bit skinny, you can just tighten it up a bit and you're still reasonably comfortable and still fits reasonably well. But, you know, if you wear extremely tight-fitting clothes and you get slightly fuller in your stomach, then, like, you know, and the clothes have no give, they're not elastic, then it just splits apart, right? So that's a sort of different. So basically it's how much give the solution has. So that's the function. As to how a buffer solution is made up, then the ideal buffer solution, so even ones that don't fit this criteria can buffer to some extent, but if you ask, like, you know, what does a buffer solution need, you basically give them the ideal one. So basically you need equimolar amounts. So equimolar meaning the same number of moles. Okay. You need equimolar amounts, you know, of a weak conjugate acid base. Okay. So the key things you need to throw in for your definition include the fact that you need a equal molar amounts. It has to be weak, can't be strong. And well, your conjugate acid-base pair is also required. So basically, more or less everything in that definition. Okay. Now, what does that mean? So, for example, I can take 0.1 mole of CH3COOH aqueous and 0.1 mole of CH3COO minus. That's what I really want. I want CH3COH, which is, well, a weak acid. And I want CH3COO minus, which is its conjugate base. Now, while CH3COO minus is what I want, I can't just have CH3COO minus by itself. That's not possible. And since I can't have it all by itself, then what that basically means then is that, you know, I need to put it as part of something. So usually, you know, while it's CH3COO minus that I'm really after, what you'll often see instead is we'll say is CH3COONA, right? And, you know, this is the aim, to get CH3COO minus. So what that means then is before we added anything, then you've got equal amounts of this, you know, in some, let's say 1 liter, it doesn't matter. And so you've got CH3COOH being happy, doing its own thing, and it will very, very slightly, you know, ionize. It will very slightly ionize. It was always not going to ionize much before because of the fact that, you know, there's, you know, like, it's weak to start with. Now, CH3CONA is going to simply dissociate. So it's going to just dissolve completely because it's very soluble. You're going to get CH3COO minus plus Na plus. Now, I don't care about the Na plus. Because this is dissolved completely, you're going to get 0.1 mole of this in solution. And because you got 0.1 mole of this, then basically thinking again from what we said yesterday, whether from Le Chatelier's principle or common ion effect or whatever, basically you already have 0.1 mole of this in solution. So this basically hardly will ionize because, you know, if there was none of this and only 1% goes across, well, now you've got 0.1 mole of this, so there's quite a lot of this. So it basically won't go across much at all, right? So more or less you've got, you know, 0.1 mole of this from the you know, sodium acetate. And if you assume none of it goes across, which is very close to the reality, then you're going to get 0.1 mole in this form, in the, you know, form that's not yet dissociated, and you're going to get 0.1 mole of this ion from the solution of that. And therefore, we've achieved the equimolar amounts of a weak conjugate acid-base pair, being, you know, this and this. And, well, we might want to think about how that actually helps us maintain a buffer solution. And again, you know, as per usual, this is partly going to be because of theory we've already covered. So consider what happens if we add a little bit of amount of acid. So if, for example, a reasonable, like not excessive amount of HCl is added, then remember HCl is a strong acid, so it will dissociate to form H plus Cl minus. But what that means then, of course, is, as I said when we did module 5, this you have to, we're adding something that technically is not a reactant. So you have to think about what happens. And in my example here, we're adding HCl, which dissociates to form H plus, which then essentially means that this goes up. And, using Le Chatelier's principle for now, essentially, if this goes up, that means, because, these are all AQ and so on, it will therefore shift left. And if it shifts left, then as we kind of showed you with our graph, at the start of today, to sort of hopefully make it clearer, that means the H plus ion concentration, because you've shifted left, is now going to go down compared to right after the addition. So therefore, the H plus ion will now, go down from the change, and therefore the change in H plus ion concentration has been minimized, and therefore the change in pH is also minimized. And very similarly, because a buffer solution is not only meant to help you with acids, it's also meant to help you with bases. So if we add NaOH, then of course, NaOH will dissociate. And then the OH minus, of course, while technically not part of the reaction, is going to react with the H plus to become H2O. And so essentially the net result of that is that the H plus ion concentration obviously you're going to get the fact that everything will just, reverse. So that means this will shift to the right. And that means H plus ion concentration will then increase, which means the change in H plus ion concentration will go down compared to if you didn't do anything. And therefore the change in pH will again go down. And that's basically how buffer solutions work. It's essentially rely on the fact that, your buffer solution is essentially, in equilibrium, right? It's an equilibrium of a weak conjugate acid-base pair. And as a result of that being an equilibrium of a conjugate acid-base pair, and, you're essentially shifting the equilibrium when you, add acid or base, and the equilibrium always goes against the change that you introduce, which therefore means essentially the net change is less than, what it would be if you had no buffer solution, if you had no buffering action.
Acetate equation, do you write it with water or do you not take account of water?
Doesn't matter.
Oh.
This is actually, oh, wait. So for this one, sorry.
Yeah.
For this one, yeah, you probably wouldn't need the water because water's not really doing anything.
Oh.
Water is doing the hydrolysis, but that's not really, unless you want to write the complex ion, which is not really required in your course. It's not really part of that. So yeah.
One more question. Does triprotic acids require more base to neutralize than monoprotic ones?
By definition, yes.
Even if
assuming the same concentration, it needs triple.
Oh, even if it's like a weak acid, like citric acid?
Doesn't matter.
Okay.
If you're calculating how much, so that might be something that we'll talk about when we do titration, but the short version is whether it's strong or weak does not affect how much you need to neutralize. Neutralize is, think year 11, year 10, just calculate the moles, that's it. That's the short version.
Okay.
Okay. So no one has any questions with what we covered thus far? Okay, So we'll move on to titration now, and that will probably, draw this module to a close. So, titration is kind of the combination of sort of various concepts that you'll need to know. But basically, I think, hopefully you guys are all quite clear with this. But I think some students get, really bogged down in the calculations, which of course you need to know, all right? You of course need to know the calculations, and of course you'll be tested on that. But I think a lot of students might struggle with just understanding what on earth you're actually doing. So titration, remember, the aim of a titration is always to, accurately determine the concentration of a solution, and quite clearly, obviously, you don't know the concentration of this solution. So whatever you're doing with the titration, that's the aim, to work out the concentration. And at sort of very basic level, at a very basic level, because, this is nothing new, you've got some solution, you've got some solution 1, you've got some solution 2, and, typical questions are going to be acid and base, but they're certainly not the only ones. But let's stick with acid and base for now. So, solution 1 might be an acid, and solution 2 might be a base. And, let's say that this is the one that has unknown, or typically, a lot of the time we might do it this way. So let's do that. So this one might be unknown concentration. So basically, just, you take the acid, which you don't know the concentration of, you react with a base, all right? So you do obviously need to know the chemical formulas for each of them, and more importantly, the number of, protons for each acid and the number of hydroxide for each acid. But, you've got an unknown concentration for the acid, and basically you know the concentration for the base. So this is known concentration. And then basically you calculate the volume, right? So you make it so that you know the volume, and you also know the volume here. And basically the very, very simple idea is, these things are going to react, and keeping it simple and you know the ratios. So obviously, things get a bit more complicated, but it could be M and N. But the point of the thing is, because you know the concentration and volume for one of the solutions, you can get the number of moles. And because you know the ratios, the stoichiometric ratios, you then know the number of moles of the, solution that is known concentration. You can then get the number of moles for the solution that is unknown. And because, you know the volume, you can therefore calculate the concentration using, N over V. That's basically it, right? I mean, as far as what you're doing in titration goes, if we're ignoring the detail, which of course there is a lot, which is what ETOG is all about, but the concept is basically something you can kind of think of from junior science in year 7, right? Your aim is to determine the concentration of something. Well, okay, well, we don't know how concentrated it is. So we'll just, react it with something. We'll know how concentrated that is to help us out. We'll measure how much of it we use, and then because we know how concentrated and how much we use, we know how much of it we used in terms of number of moles. We know the ratio, so we know how much there must have been. We know the volume, so we can then calculate it. And so you just, just react them until you're done, and you're it, and that's it, all right? And that's the concept, and it's really easy. That is just the concept. Of course, your course goes into a lot more detail than that, and obviously we need to talk about that, but that is the concept. The thing that makes all the detail basically is this word. You want to do it accurately. So rather than just go and give you this wishy-washy idea of, what we're doing, we now have to define everything accurately to a high degree of precision. And so that's where, we have to start asking questions like, well, how do we measure volume accurately? You know, how do we know when to stop accurately? Like, how do we know we didn't go over by a lot? You know, how do we reduce errors in procedure? So really, the concept itself is not hard. The concept is really simple. The problem is, now you want to do it accurately, you basically now have to basically, you know, look at every single aspect and try to minimize errors in every single possible way. And that's where all the detail comes in. So perhaps we'll start with, you know, starting, you know, with your some jargon now. So your standard solution, of course, is by definition a solution whose concentration is known. You know, to a high degree of accuracy. And this is where, you know, you have two types of standard solutions. You'll have either, you know, two types. You'll either, you know, have them be primary, or it could be secondary. And if it's a primary one, basically you made it. You made the primary solution. So, you know, you dissolved a certain mass into a certain volume, and then, you know, calculated the concentration. All right. And that in and of itself has a whole lot of steps, right? So I might gloss over that for now, depending on how we go. But this itself, again, because you're trying to do it accurately, has many considerations. And you can be tested on that, right? You could be tested on how to prepare a standard solution. And by that, that would mean a primary one. Or the alternative is a secondary. And so a secondary basically is, well, you know, we didn't make it. We worked it out what the concentration was. So essentially, this is a solution whose concentration was not prepared. You didn't make it, but rather was determined by another titration. So basically, you did a titration, you worked out what the concentration was, and now you are now saying, okay, because I worked it out, I know what the concentration is, and now I'm using that as a standard now. Whereas a primary is, I have no idea what the concentrations are, I'm going to make a solution, I'm going to dissolve this number of grams in this amount of water, I'm, you know, taking all the necessary precautions for a primary standard, and therefore once I've prepared it, you know, I know the concentration, right? So perhaps I'll briefly run through the considerations for primary, but I'll go through it in less detail than I would if you need a bit more detail about all the sort of, you know, practical steps and so on, that you might want to do that. But basically, considerations include, you need to sort of, it starts by the choice of the substance. So you can't just pick anything. There's multiple considerations you need to sort of understand. So it clearly has to be very soluble, obviously. And it needs to have a known chemical formula, which appears to be sort of quite obvious, but, you know, you might not know the chemical formula for everything in real life. You must also be able to obtain it with high purity, which again can cut things down. And from a chemistry point of view, it must be stable. And that means, you know, you can't react it with air. Would be a no-no. It needs to be stable under heat, because you might be, you know, unless you want to keep it refrigerated the whole time, for example, it must be stable under light, and so on, etc., etc. So lots of considerations there. And another thing you need to be concerned about, and this is very often tested, is whether it's hygroscopic. And so it can't be hygroscopic. So I should probably write, is not hygroscopic. So hygroscopic is basically just a fancy word to describe whether it's going to absorb water. And, you know, it might absorb water from, you know, the air and so on, and that will clearly affect, you know, the concentration because you've just got more solvent. So a very commonly tested thing is, why is sodium hydroxide never a standard solution or never a primary standard solution? Well, the biggest reason is because it's quite hygroscopic. So, you know, that's the primary reason why NaOH is not suitable for this reason. I mean, there are other reasons, but this is the primary reason. Now, you might say, well, but we use sodium hydroxide all the time as a standard solution. Yeah, you probably did, right? You probably did do sodium hydroxide as a standard solution. You probably used sodium hydroxide here as a base, and you probably used phenolphthalein as an indicator, and you reacted with, you know, some acid, such as hydrochloric acid in the most simple case. But that's because you were told what that concentration was. And that's because someone else did a titration at some point in time before they gave it to you to work that out. They didn't take sodium hydroxide and dissolve it, or most of them, they shouldn't do that. They had that solution prepared, they did a titration on it, figure out the concentration for you, and said, here you go, here's a number. You're using it as a secondary standard solution. Okay. So firstly, you have to pick the substance, and then, well, I'm summarizing very briefly here, but basically, you know, then basically, you know, the steps are to prepare it gravimetrically. And basically, you know, you have to measure it out. You have to measure the weight. You measure the weight. You have to, you know, and you'll need to obviously transfer it appropriately. I'm more or less skipping that, but the key points are that you need to make it anhydrous. And so basically you need to heat it and remove the water. And that's another reason why you want it to be stable under heat, because if you're doing it this way, you don't want it to decompose while you're heating it up. You know, you don't want to, you know, remove the water, but in the process, change the chemical formula by decomposing it. So, you know, has to be, you make it anhydrous. And then, you know, when you work out the number of, like, when you dissolve it in water, you know, that is the key idea. You know, you measure something and you dump it and you dissolve it in water. But again, because of accurately, you know, you use a volumetric flask rather than a beaker or anything like that. Okay. So those are the basic steps for your standard solution. Now, as far as titration goes, again, always because of all the sort of, you know, accuracy things, we're going to now have to use special, much more accurate and relative to beakers and so forth, much more expensive equipment. So you'll have your different types of equipment, right? Oh, conical flask is just there, right? So you'll have what's called a pipette. You'll have what's called a burette. Those are highly accurate. And this is just your flask. So the purpose of a pipette is to measure a fixed volume. Your burette is to measure variable volume. And your flask is pretty much just to, you know, allow, you know, a place for the reaction to occur. But of course, you know, I mean, why don't we use a beaker? Well, I guess, you know, there's a few things. Like one, you can see quite clearly. So, you know, clear observation. And given the sort of narrower thing up here, it helps you swirl, you know, allow swirling. Right, to evenly mix it. So there's a few different reasons why I would do that. Let me save a bit of space here. So, all right. And of course, you need to know the preparation procedures for each of them as well, right? And that's, you know, commonly tested. And so note that as far as your preparation procedures go, you will always rinse them with, you know, water first, all of them. So rinsed with, you know, I'll write it out on the flask, all right? I'll just write water for the others. So rinse with distilled, deionized water. Now, you know, some teachers might say, you know, rinse it 3 times or anything like that. I don't think, you know, HSC really cares how many times you do it, but just, you know, and you might get away without saying distilled deionized, but better to put it in, all right? So basically, rinse all of them with water, all right? Now, in the case of the conical flask, that's it, you're done. No other steps. You know, obviously dump the water out, right? But, you know, you might have a few drops of water in there, and, you know, some people feel like that's going to affect things, and the answer is it doesn't, all right? So we'll just say quite clearly, it doesn't. You can leave a few drops in there, not a problem, all right? Maybe we'll talk about the wine in a moment, but let's just focus on this for now. So the pipette, you're going to rinse it with water, and for a pipette, there will be drops of water staying in there, and, you know, it will affect things, because for the pipette, you're going to fill it up with your acid or your base, and, well, clearly, you know, if you've got water in there, it's going to affect the concentration and more importantly, the number of moles of the acid or base. So you basically then rinse with whatever solution you were going to fill it up with. So rinse with the solution that you were going to measure. And so now, because you've rinsed it with the solution you're about to measure, so don't fill it up, but just rinse it, then hopefully all the water has now left, because, you know, you rinsed it with a thing, and what's left are drops of the solution you wanted to fill it up with. So now it no longer matters if it stays, because it's the same thing anyway. And so now you can sort of fill it up, and, you know, fill it up so that the bottom of the meniscus is level with a calibration mark. And pipette burette is the same thing, right? You don't rinse it. So whatever you want to put in the pipette, rinse that solution through the pipette. Whatever you want to put in the burette, rinse that solution with the burette, right? And then fill it up. And the whole point of using these, as opposed to your typical measuring cylinder and, you know, things like that, is, well, not only can you just, you know, change the volume by dropping it out and so on, but more importantly, these are designed to be highly accurate, okay? And that's one way to reduce your, you know, error, by using better equipment, right? They measure volume more accurately compared to things like a measuring cylinder and so forth. Okay. So the next thing after that then is, well, we've got, we basically will think of, like, let's think of the errors, because that's also typically sort of done. So imagine I had, you know, I'm going to have to define a reaction to make it simple. So I've got acid plus base, and I'm going to say that the acid is going to be put in the pipette, and I'm going to say, therefore, that's known volume. And I'm going to put the base in the burette, and that's obviously going to be a variable volume. All right, so in this situation here, then the question is, if I've got the acid in, and, you know, I go and react and I've got the appropriate indicator, and that's something we'll need to talk about in a moment. But if I, for example, did not rinse it with, so obviously in my example here, I should rinse it with water and then with the acid, and then do it. But if I rinsed it with water and I did not rinse it with the acid, whereas I did everything else correctly, then if you think about it, the question is, how does that affect my result? So in this example, example 1, if the only error is the pipette was rinsed with water only, and, you know, it should have been followed up by the acid, but it wasn't. So that then means that some drops of water are in there, not much, right? But there'll be some. And so when you fill it up, that means you're going to have less acid, right? compared to if it was all acid. And if you're going to have less acid, that means the base that you need to add is going to be less, right? So you're going to be adding less base. And imagine that, you know, this is the standard solution. Imagine the base is the standard. So let's say it's sodium hydroxide is a secondary standard. So that means you're going to use less base to neutralize, which means you're going to think that the acid is less, you know, it's going to basically affect the acid. You're going to incorrectly believe that the acid is more dilute. And very similarly, if your burette is rinsed with H2O only, in my example, then that means your burette will have some amount of water in it, not much, but it will have some, which means the whole thing will be relatively less concentrated. And if you've got a solution that's less concentrated than what you thought, then that means you're going to need to use more of it, but you don't know it's less concentrated, just, you know, you're going to use the concentration from your standard. So you're going to use more of it. And because you're going to use more higher volume of base, you're going to think that you need more base to neutralize the acid. And so you're going to incorrectly calculate that the acid is more concentrated than it actually is. You're going to overestimate the concentration, all right? And then to be perfectly clear, if you do that with a flask, I won't write it out because I'm running out of space, but you know, if you do that with a flask, it doesn't matter, because let's say if this was done properly and this was done properly, then the pipette is 25 mils and you dump your acid in there. So you've got a certain number of moles of acid in there. Yes, it's diluted by the water when you dump it in, but who cares? It's got the same number of moles. Now your burette, you know, having a certain, you know, is also unaffected. And so you're just going to need to dump the same amount of volume for the same amount of concentration in there as well. And so your volume, which is read off from the burette, and your volume, which is read off from the pipette, is not going to change despite the fact that you've got water in the flask. So a few drops in the flask really doesn't matter. In fact, theoretically, more water in the flask really doesn't matter. But obviously, the more water, the more dilute. It will be more dilute here. It just won't change the number of moles. And if it's more dilute, then the slower the reaction rate. So that means if you had more water, which you don't want any in the first place, you're just going to need to be even more careful with your titration. Like if you have, like, you know, lots of water, you just need to give it more time to react. But theoretically, other than the practical aspects like that, it's not going to affect anything. All right. Now, another point that we need to talk about is how do we know when to stop? And that's going to be, by definition, the equivalence point. So the equivalence point, by definition, is the point, you know, where, you know, you have fully neutralized, no more, no less. So there's no excess acid or base at all. Now, unfortunately, we don't know when that is. We know theoretically when that is, but we don't know exactly, like when we're adding acid or base, and that's kind of back to our earlier you know, thing, how do we know when to stop? Because yeah, we will just go, we don't want to add too much, but how do we know how much that is? Because sure, it might not react anymore, but you don't know if you added too much by like a milliliter or like half a milliliter or one, like, you know, you don't know. And that's true, you don't know, right? That's the equivalence point, but you don't really know that for sure. And since we don't really know that for sure, we introduce a concept called the endpoint. So the endpoint, by definition, is the point when the titration stops. And that's when you stop adding. And of course, the aim is to let the endpoint approximate as close as possible, and you can get very close if done appropriately, the equivalence point. So the endpoint is up to you. You decide that. The equivalence point, you know, is set. I mean, but you don't know what that is, right? But you set the equivalent, the endpoint, and you basically need some signal to tell you, okay, stop the titration now. And you know, typically, the typical example, but you know, there are other ones, that you might have come across in module 8, for example. But typically, that's when you change color. Indicator changes color. But there are also conduction ones. There are also precipitation ones, and so on. So, but the idea is there's an endpoint. And so, if we're looking at acid-base titrations, what you need to focus on, therefore, is the choice of indicator. And summarizing very, very, basically here, basically this depends on the strength or weakness of your acid. So if you've got a strong acid plus a strong base, then you'll end up with a neutral salt. So basically, if you've got an acid and a base, we know we'll end up with a salt plus water. And really, if you have neutralized fully at the equivalence point, you're not going to have any acid or base left. You're only left with the salt. You're only left with the salt. So really, this ties into your theory about whether your salt is acidic or basic, right? You're only left with the salt. So strong acid plus strong base will give you a neutral salt. And that's why we would therefore, in this case, pick an indicator that is going to change around neutral point. And therefore, your typical choice would therefore be bromothermal blue. And, if we had a, I'll just abbreviate it. So if you had a strong acid plus weak base, then you're going to get a salt plus water. But because it's a strong acid plus weak base, and, you can go into the explanation and so on, but basically, strong acid plus weak base will end up with a acidic salt. And because you've got an acidic salt, then what that basically means then is that you'll end up with a, you'll need to get one that changes in an acidic range. So your typical choice there will be methyl orange. And of course, you've also got, strong or weak acid plus strong base. And that will give you a basic salt plus water. And that is why typically that one you'll use phenolphthalein. And that's why those are your typical indicators, and you have to know their change ranges and when to use them and their colors, which we've covered before. And just so you know, weak acid plus weak base does exist, but this is typically not examined just because it's much harder. And you're not going to rely on just a simple color change. You're going to use like a pH meter and graph out the pH curve and all that kind of thing. And I'll quickly draw up pH curves to sort of indicate, but basically if you've got, but you also have ones on conductance and so on. So just briefly, if you've got if you start with like a strong acid and you're adding NaOH, like there's the volume of NaOH added, and you're doing a strong acid plus a weak base, then obviously the pH will start quite low and it will kind of do this kind of thing. And the key point is it's going to start from the gradient is very vertical for a large range. And that's why it doesn't matter too much whether you pick a, one that changes at around 3 or around 7 or around 9, it's all going to give you the same volume basically. Whereas if this, strong acid plus weak, plus strong base, now that's usually too easy. They're usually not going to test that, right? But you could also have a strong acid plus weak base. So that's going to start low. And because it's a weak base, what will end up happening is you'll go up, but not quite as far. And then it'll kind of do this. All right. And so, and it won't go that high either. Like you'll maybe stop at around the sort of 9 or 10 mark, right? And so, but you will, by the way, see this sort of buffering action here. Okay, you can see this sort of, because it's a weak base. But importantly, you'll notice that this change range is probably from around like 3 to about 5. And that's why you need to pick your endpoint to be around here, because if you pick your endpoint to be around, let's say 7, you're all the way over here. And if you picked it around 9, it's all the way over here. So that's why, and clearly, the equivalence point is here, no matter what indicator you picked. So you want the indicator to, indicator to be around 3 to 5 for the change. All right. And of course, you've got the alternative, which is weak base plus strong acid. So because it's a weak base, you'll end up seeing that it has this sort of buffering action, and then it will sort of break down, and then it'll go high. But because it's a weak base, it will start relatively high, so maybe like around 3 to 4, and then you will change this at around 7 to around 9. And so for the same reason, that's why you want your change range to be at a 7 to 9, not earlier, because otherwise you're going to get a big difference here in sort of your volume, and you don't want that, obviously. Great. So that should more or less have covered the key parts of Module 6, and we'll pretty much leave that there today. Does anyone have any questions?
Oh, yeah, yeah. What is the last graph for?
What do you mean?
What weak acid plus strong acid? Or...
Oh, right. Sorry. Plus strong base.
Oh, weak acid plus strong base.
That's why, you know, it changes that way.
Right. Is it at 14, like 13 or 12? The top part of it?
The top part of it will, well, depending on the concentration of the base, but yeah, it can reach that. But, you know, the range is like around 9. The change is to around 9, and then, you know, this would go depending on, you know, the concentration of the so forth. But yeah, it could be, you know, reach like 13, 14, so on. Are there any other questions? So you know, in terms of calculations, you know, we can definitely do some titration calculations there. So we might do that, say, tomorrow. Now, I can send you guys a sheet if you guys work with titrations. So I'll just stop that there.